Hi, everyone. Welcome to the Monday seminar. Super excited to see people and to be here today with Eric Beaucé. The seminar series has been going on for a while. I assume most of you are familiar with our normal mode of operation. We ask people to mute themselves at the beginning, but we encourage people to interrupt with points of clarification along the way. So that we've all given talks to Zoom into our screen in a room all by yourself. It's kind of nice sometimes to have some feedback. So if you have a point of clarification or some minor thing you'd like to bring up, I think Eric would be quite happy to be interrupted for that. But then save your real questions and discussion points until the end. And we really do encourage everybody to participate in that. There's often quite a while for that, 30 minutes or so, but it depends on lots of things. So without anything further, I will turn the floor over to Eric. Thank you very much, Eric, for being here and for putting together, looks like a great talk. Go ahead.
Well, thank you, Chris, for inviting me, and thank you all for attending my presentation. Today, I'm going to talk about probing fault systems with the tides, with an emphasis on the preparation phase of the 2019 Ridgecrest earthquake. All right. So first, I'm going to start with a broad introduction about strain localization and rock failure, link it to preparatory phenomena, and especially to the tidal modulation of seismicity before large earthquakes. And first, I want to define what I mean by the preparation phase of large earthquakes. And for that, I need to talk about the concept of the seismic cycle. So as I think most of you know that very well, the shallowest layer of our planet, the crust, is always in motion. And this motion induces deformation that localizes in weak zones that we call faults, and which look like that in nature. So now if I represent these faults schematically, well, at these faults, we have two crustal blocks that stick to each other because of frictional forces along the fault, while tectonic forces want these blocks to slide past each other. And so after years of deformation, the tectonic forces are so high that the fault breaks. And when breaking, slip happens so fast, within seconds or minutes, that it generates waves, and that's what we call an earthquake. Deformation in the field may look like this. And of course, we all know that large earthquakes can lead to major disasters. So the seismic cycle is the name that we give to this cycle of accumulation and relaxation of tectonic forces along faults. And my research focuses on the preparation phase, which is at the end of the seismic cycle. It's a phase whose duration is poorly constrained, and it's a phase that supposedly is associated with precursory phenomena that are related to the fact that during that phase, tectonic stresses are high, and also the amount of damage in the fault zone is high. So faults are on the verge of breaking. And at the very beginning of the question of the preparation phase is the question of what happens to this rock under increasing compression. So you probably know that the rock is going to break, but the question is, how does it break? And detailed imaging of damage in rock samples tell us that failure does not happen instantaneously, but instead failure results from the localization of strain in space and time. So first, cracks form, and cracks interact to form small faults, and ultimately small faults coalesce together to form a large-scale fault that caused the large-scale rupture of the rock sample. So the point I want to stress here is that rupture is a bulk process. Even if the process collapses in 2D onto a fault plane in the end, it is otherwise a bulk process. And these experiments by François Renard et al. Also teach us that the manifestations of strain localization vary based on rock properties like porosity. So already in the lab, things are complex, so we can expect this complexity to be even higher at the scale of natural faults. All right, so large ruptures, so like large earthquakes, result from unstable strain localization, which is seen as the creation and the increasing concentration of damage in the fault zone. So we can expect the properties of the crust near the fault to evolve with time. And that's how we hope to detect the preparation phase. And as an observational seismologist, I try to decipher the seismic records to find and understand preparatory phenomena. And these phenomena really are the key to physics-based earthquake forecasting, because if there are signs of an upcoming earthquake, then we can anticipate it. And these preparatory phenomena are well observed in the lab, but they remain really elusive in the field. If there are preparatory phenomena, and if we could systematically detect them, then we would be able to forecast earthquakes on a physical basis and anticipate disasters like this. So the question of the preparation phase has very high scientific, but also societal stakes. And that's why for the past 50 years or so, we've seen papers come out in Nature and Science every time a new precursory phenomena is identified. But the issue with this observation is that they are not systematic, they are false positives, and more importantly, there is no established physical model to explain these observations. So we need to do better, and of course, all these previous contributions help us move forward. Right now, there are interesting leads emerging that I will follow to contribute to making these observations systematic and understanding the physics. And here I want to take the example of the 2011 Tohoku earthquake, which was a giant earthquake of magnitude 9 in Japan, and it caused the Fukushima disaster. So after the fact, there were reports of precursory phenomena happening on the timescales of months to the timescale of just a few hours before the main shock. But now there is this study by Tanaka that really stands out from others, because here Tanaka shows a precursory signal over the timescale of a decade. So Tanaka shows that seismicity synchronizes with the tides, and the signal of synchronicity becomes more and more evident as time evolves towards the main shock. So the tides are caused by the gravitational attraction of the moon and the sun, which cause really small stress perturbations in the crust. But still, that is enough to modulate seismicity, but we're talking about a really subtle signal of modulation. And Tanaka published similar observations for the other giant earthquake of the 21st century, the 2004 Sumatra earthquake. And despite the almost unbelievable nature of these observations, a similar phenomenon was reproduced in the lab, like in these experiments led by Christelle Chanard. And these experiments consisted in deforming rock samples of a few centimeters long, using a background stressing to bring the sample to failure, and on top of that, use an oscillatory forcing to study the modulation of laboratory nano-earthquakes as the sample approaches failure. And they observe, like in the studies of Tanaka, they observed that this modulation increased as the sample reached failure. So the issue here is that Tanaka's results had never been reproduced with any other earthquake. Until recently, when my collaborators and I actually revisited the question targeting a large earthquake, but not a giant one like Tohoku or Sumatra. And so an excellent candidate for that was the 2019 Ridgecrest earthquake in California, which had a magnitude of 7.1. So here, the first thing we did was to build a new earthquake catalog covering 10 years before the main shock. And for that, we used machine learning and other cutting-edge techniques to detect and locate as many tiny earthquakes as possible in the study region. And using this workflow BPMF that I have developed over many years, we could detect 40 times more earthquakes than were in the conventional catalog, which here is the SCSM catalog. And of course, the reason for this increase is that by using new detection techniques, we could find small earthquakes that were previously missed. And that's a huge gain of information, because smaller earthquakes reveal the physics at smaller scales. And thanks to this new information, we could observe the tidal modulation of seismicity. And for the first time since Tanaka studies, we could observe the increasing modulation before a large earthquake. So these results are very important. First of all, just because we're adding another observation of the tidal modulation of seismicity, which in itself, it's a phenomenon that has been debated for decades. But most importantly here, these results show a long-term precursory signal taking place over several years on an earthquake of magnitude 7, so about 100 times smaller than Tohoku or Sumatra. So here, this study really opened the way to systematizing these kind of observations for earthquakes that are relatively frequent. And here I just wanted to very briefly summarize our previous study from 2023. I know that it might have been a lot of information at once, but actually I'm going to come back to this concept all along my presentation. So because of the important implications of this 2023 study, it actually it underwent close scrutiny by the community, and there were some questions and concerns that were raised after the initial study, and here I'm summarizing some of them. First, the question is, did this signal of modulation increase really originate in the fault zone? And related to that question is, was there some sort of leakage from earthquakes located in the Koso volcanic field, which we could have just mislocated? And so the concern is that because earthquakes in geothermal sites are highly sensitive to the tides, we could have just been corrupting our signal. Beyond that concern, my own question is, what is the role of the Koso volcanic field and heat mining in this story? And finally, the question, a question that came several times was what happened with the aftershocks of the Ridgecrest earthquake? So if you want to know the answer to these questions, I invite you to stay until the end of this talk. And beyond just this aspect of the follow-up study on the Ridgecrest earthquake, I want to stress here that my research really is driven by the question of what is the physics behind the increased response to the tides. Is it something related to damage accumulation and mechanisms like static or dynamic fatigue? Are we seeing the effects of dilatancy and changes in the proelastic behavior of the medium? Or is it something like the nonlinear response of the fault gouge that evolves in the preparation phase? And so unfortunately, it's not today that I'm going to give clear answers to these questions, but it's really what I have in mind when I do this research. Now I'm going to talk about what we know about the mechanics of tidal modulation and how we observe it. So as I said, the tidal stresses are caused mostly by the gravitational attraction of the moon and the sun, but also from other celestial bodies. And we are actually able to model these stresses very accurately. And so here at the top, I'm showing an example of 30 days of tidal stress, of tidal Coulomb stress on a given fault. And here you can see that the peak-to-peak amplitude of this time series is very small. It's of the order of 1 kilopascal, which is 1 kilopascal. It's about 1% of the atmospheric pressure. It's very small. But a change of 1 kilopascal over a few hours gives a stress rate that is actually larger than the tectonic stress rates. So the stress rates are quite large. And I would also like to draw your attention to the shape of this time series. This is a non-harmonic forcing. All right, so this is just summarizing what I've just said. There are many different periods mixed in this time series. So most of what we know about the effect of this forcing on seismicity come from laboratory experiments. And at the end of the 90s, Lochner and Biller conducted these experiments that led the foundation for our canonical understanding of modulated seismogenesis. So they conducted these experiments with dry westerly granite, and they found two modulation regimes that were controlled by two different timescales. The period of the forcing, T, and this time, Tn, the nucleation time, which is the time that can be measured in the lab. And it's the time when failure nucleates and a slip on the fault patch starts accelerating. They found that for fast forcing, the peak in seismicity aligned with peak stress, and that's what they call the nucleation-dominated regime. And they found that for slow forcing, peak seismicity aligned with peak stress rate. And they showed that this was consistent with a simple threshold failure model, meaning like a Coulomb-like failure model. And here I want to mention that these observations are consistent with the predictions of some numerical models, like those of François Petrelis et al. But of course, we know that the crust is not dry, and we actually really like to talk about the importance of fluids in our discussions. So the question of what happens now in rock samples with pore fluids is an important question. And so I'm going back to these experiments by Christelle Chana et al. And their observations strikingly contrast from the observations of the experiments I showed just before, because they observe a peak in activity of acoustic emissions, not at the peak Coulomb stress, not at the peak stress rates, but instead it's when the pore fluid pressure drops. And to make the picture even more complicated, I'm gonna show other experiments led by Corentin Noël, where again, here they modulated the pore fluid pressure in their rock samples. And they observed a range of different behaviors depending on the period of oscillation and also on the applied stress. So for slow oscillations, their results can actually be easily understood in terms of Coulomb stress because they observed a peak in activity at the peak Coulomb stress, so the peak pore fluid pressure. But otherwise, it's often not that simple. And so I think that all these experiments highlight the fact that poroelastic effects are complex, and bearing in mind that tidal normal stresses are usually much higher than tidal shear stresses, I think that we must expect the tidal modulation of seismicity to be highly complex. So to summarize the situation here, we saw that rock type affects the patterns of damage accumulation. Two modulation regimes were identified in dry rock samples, and then many pore pressure-induced modulation regimes were identified in rock samples with pore fluids. On top of that, these experiments have only investigated the influence of harmonic forcing, although, as I said, the tides are non-harmonic oscillations. And so if the Earth responds in a nonlinear fashion to this forcing, then it means that it's going to be hard to extrapolate the results from the experiments to natural faults. And so I hope that you enjoy this really brief tour of the literature, because the conclusion, at least from my perspective, is that we just don't know what patterns of tidal modulation we are looking for. So if we decompose the rate of seismicity into a tide-independent rate and a modulation rate, it means that we don't know the functional form of this modulation rate term. But still, the question remains of, even though we don't know what it looks like, the question remains of how do we observe this modulation term? Okay, so as I said, we can model tidal stresses very accurately. And actually what is harder is to decompose the tidal stress tensor into a normal, a shear, and a Coulomb stress component, because that requires knowing the orientation of all the faults of interest. And usually in an earthquake catalog, we just don't know the orientation of all these faults, especially for very small earthquakes. So the best we can do is to consider the optimally oriented faults in the regional tectonic stress field. And then we can compute things like the tidal Coulomb stress on that fault. So at the top, I'm showing the stress amplitude. At the bottom here, I'm showing the stress phase because, as I will show later, it's convenient sometimes to consider the stress phase rather than the amplitude. So for a non-harmonic signal, we use this instantaneous phase from the Hilbert transform. It's a phase that is equal to 0 at the local maxima and plus and minus pi at the local minima. And then it's equal to minus pi over 2 when the stress rate is maximum. So now we can extract the values of stress amplitude and stress phase at the timing of every earthquake in our catalog. And so at this point, we have all the data we need to observe the tidal modulation of seismicity. Now we just need to choose a methodology to make that observation. And there is actually no consensus on the methodology that one should use. Historically, the Schuster test, which goes back to the end of the 19th century, this Schuster test has been one of the most popular methods, although it's actually formulated for a harmonic forcing, and it's purely statistical. It gives no physical information about the modulation. This test was generalized to the Schuster spectrum, which allows to analyze multiple harmonics, but still this is a statistical test. It does not give information about it does not give physical information about the modulation. And so here we are going to directly estimate the modulation term from the data. And so this approach really embraces the full complexity of the forcing and also the full complexity of the response of the system. But of course, this is challenging. And this is challenging, but here I'm going to present the solution that I use to produce the results that I'm going to show next. So this methodology was initially developed in our 2023 study, but we keep improving it. And first, I'm going to demonstrate the methodology with a simple scenario where there are lots of earthquakes, which make it easier to detect the modulation of seismicity. So each of these black dots here shows the tidal Coulomb phase at the timing of an earthquake. So let's say that here we take a time window, let's say a short time window of 3 months long. And in this time window, we simply count the number of earthquakes in each phase bin. And we build this blue histogram. And as you can see, this blue histogram roughly follow the shape of this black dash curve. And this black dash curve is a reference curve that is simply proportional to the time spanned by each phase bin. So because the forcing is non-harmonic, some phases occur more frequently than others, all right? And so there are naturally more earthquakes falling in these time bins that cover a larger time span, but it has nothing to do with modulation. It's really just related to the temporal size of each bin. So to get to the modulation, we actually need to correct for that. And so we'll be studying the ratio between the blue histogram and the reference curve. And that's what we get on the right. And the line 1 represents tide-independent seismicity. Values above 1 means that there are more earthquakes than expected for a tide-independent process, and vice versa. If it's below 1, it means that there are less earthquakes than expected. So actually here, this ratio is extremely noisy, and here we couldn't really say anything about the physics of the modulation. This is because catalogs are dominated by a lot of seismicity driving mechanisms other than the tides. And the tides actually are one of the weakest driving mechanisms. A catalog is actually usually dominated by temporal clustering. So we need to find a way to denoise our estimate of this ratio. One simple solution would just be to increase our observation period. So instead of using a 3-month window, we could use a 3.5-year window. And you see that the ratio, the shape of the ratio really changes. And now we could start seeing emerge some kind of a cosine shape where we see a peak in seismicity around the phase of 0. And again, 0 corresponds to local stress maxima. So that makes sense. We can actually do even better. And this is the solution that I'm proposing today. We can stick to the short window, but now instead of using only one short window, we can slide that short window across the catalog. And for each sliding window, we obtain a noisy estimate of the ratio. And in the end, we aggregate all these noisy estimates, either using the mean operator or the median. And here we use the first singular vector of the SVD. And again, I'm going to switch back and forth. So here, the ratio gets slightly cleaner. We don't see a huge improvement because we are in a simple scenario where detecting the tidal modulation of earthquakes is simple. But that's the methodology that we're going for. And this ratio here is our estimate of the modulation term. And to further motivate the use of this methodology, I'm now going to show you exactly the same series of figures, but for a more challenging scenario. And challenging just means a sparser seismicity, right? So from 11,000 earthquakes, we go to slightly less than 2,000 earthquakes.
Eric?
Yes.
All right, Chris, just to interrupt for just a second. Can you remind us what you have done with the catalog? Are you using the seismicity in a certain depth range? Maybe you said and I forgot. Or using all the seismicity, and what do you assume about the orientation of the faults? I know you said something about orientation, I didn't quite catch it.
All right. So okay, so here I'm just exposing the methodology, and I'm gonna go back to the results about Ridgecrest in a moment, and I'll keep these questions in mind, and I'll make sure to answer them clearly.
Thanks.
Okay. So yeah, just finishing with the methodology. Here is an example with fewer earthquakes. And so of course the ratio here is extremely noisy for the short window, for the long window as well. But now we see that with this multiple short window approach, now we see something we can work with, where we see more earthquakes at the negative phases. So we have a technique to observe the modulation and to estimate the tidal modulation term. Now the question is, how do we characterize this modulation to extract physical information about the underlying system? And I'll get to the results in a moment. So today I'm only going to present results based on this kind of empirical model that imposes a cosine shape to the ratio, where alpha here is it quantifies the strength of modulation, and phi 0 gives the position of peak seismicity within the tidal cycle. I actually prefer to use a slightly more generic version of this empirical model, which is expressing it in terms of an exponential, which allows us to deal with cases of very strong modulation. And also it makes more sense in terms of rate and state friction, although I'm not gonna discuss that in detail today. But for weak modulation, these two models are the same. So the strength of this empirical model is that it requires no prior knowledge, or let's say almost no prior knowledge on the modulation regime. It can characterize stress control regime or a stress rate control regime, but it comes at the cost of an unclear relationship between the phase and amplitude, right? Because, for example, at local maxima, the forcing actually takes a range of different values. And then I say almost no prior knowledge because we still impose that the modulation regime has a unique peak, which may not be true in nature. So to go back to the two examples that I just showed, using the empirical model, we see that the modulation strength is similar for these two examples, but the modulation regime is different. Here, in one case, we have a stress control regime because phi 0 is close to 0. And here we have a stress rate control regime because the peak seismicity falls at the peak stress rate. Okay, so now all of that takes me to the case study of the Ridgecrest earthquake. So Ridgecrest is located. Ridgecrest is located in Southern California. It's located in this in the Eastern California shield zone, which is actually where all of the major earthquakes occurred in California in the past 30 years. I recall that the goals of this follow-up study is to confirm the tectonic origin of the signal of modulation increase before the main shock, and we want to discard the possibility that there is some corruption due to earthquakes happening in Coso, located just northwest of the fault zone here, and I forgot to put it on my map, but it's located just here. You'll see it in later maps. And we also want to clarify the role of the Coso volcanic field in our story and investigate aftershocks. So in the initial study, in the 2023 study, we restricted ourselves to this rectangle here. But in the follow-up study, now we're using the seismic data from everywhere in this region here. So using this additional seismic data and using a slightly updated version of the detection and location workflow, we could dramatically reduce noise in earthquake locations. As you can see here, the picture now is much cleaner. Also, actually adding more stations effectively made detection thresholds more conservative, especially with techniques like template matching, which is part of the detection workflow. So as you can see in the box taken along the fault that broke in the Ridgecrest earthquake, we now have 9,000 earthquakes over 10 years before the main shock, against we used to have 27,000 earthquakes. We also have a preliminary catalog for the aftershocks of the Ridgecrest earthquake. And I say preliminary because we've only applied half of the detection workflow, really for computational limitations. We'll need much more time to run the entire workflow. But the rates of seismicity were so high after the main shock that we already have many, many earthquakes in this catalog. And as you can see here in the box along the fault, there are 140,000 earthquakes over 4 years. And so to achieve the goals that I just mentioned, we'll be looking at the tidal modulation in 5 different regions. So I define 2 boxes that look at the fault zone. There is one box that will be taken across the entire fault zone, and one box that stops, that does not include the northernmost events. And we'll use this southern box to make sure that the signal in the fault zone is not dominated by these northernmost events, which one of the concerns that were raised was that these events might be corrupted by Coso. And then we have 2 boxes for Coso. So the small blocks here is the Coso volcanic field itself. That's where heat mining is happening. And we're also defining this larger box that takes all of this region of high seismic activity that seems to be associated with geothermal activity. And then just north of the fault zone, we define this box north of fault zone, which also is an area of high seismic activity, and we'll be using it as kind of a control study. All right, so before looking at tidal modulation, there are actually a lot of things to look at in these very detailed earthquake catalogs. And so here I want to show you some very first order features of the seismicity. And namely, that is the cumulative number of events as a function of time taken in these 5 different regions. And here I'm separating it into 3 different depth intervals. And in terms of shear numbers, we see that the COSO region dominates all the others, at least for the shallow seismicity. But then for the deep seismicity, so deeper than 15 kilometers, we see that there are lots of events in the fault zone. And I'm sure that you've already seen it. There is this really interesting feature where we see accelerating deep seismicity before the main shock, at least 1 year before the main shock, and probably starting before 2018. And it's even more apparent if now I plot the normalized cumulative event count. And we even see that COSO seems to be affected by this accelerating deep seismicity, even though in terms of absolute numbers, there isn't much happening at depth in COSO. So I think that in itself, this observation of accelerating deep seismicity in the fault zone indicates that there is some tectonic process going on at depth. And now we're going, I'm going to switch back to the topic of tidal modulation. So to answer Chris's questions, I'm actually not doing, at least today, I'm not doing any separation in depth. I'm just considering the seismicity at all depth for every of these 5 regions. And I'll be considering the optimally oriented faults in each of these 5 regions. So I know the tectonic stress field in each of these regions, and that's how I can estimate the optimally oriented faults. So I applied the methodology that I described earlier to each of these 5 regions. And I recall that each estimate of the modulation term is built with this the sliding short window approach that effectively senses a total of 3.5 years. So each estimate is built from 3.5 years of data. And so to get to the tidal modulation as a function of time, we need to slide this 3.5-year window at all the different times of our catalog. And we build observations that look like that. And so each column here is a modulation term. And now the height of this modulation term now is color coded. So red color shows the phases when there are more earthquakes than expected for a tide-independent process, and vice versa. Blue colors show the phases when there are less earthquakes than expected. And we use the empirical model to characterize the tidal modulation. So I forgot to say that, but that's an analysis in terms of the tidal Coulomb stress phase. And so with this empirical model, we get a time series of model parameters. And so, for example, here in this region, the time series of modulation amplitude looks like that. And I'm going to comment on trends later. Here, I just want to show you more of the raw data before going further. We also did the analysis in terms of the tidal volumetric strain. All right, so you see, we see almost the same results. All right, which is in a way it's great because the volumetric strain Now this is an invariant of the strain tensor. It does not depend on fault orientation. So looking at volumetric strain eliminates one possible source of errors, which is the possible errors in fault orientation. But the fact that the results in terms of volumetric strain are very similar to the results in terms of Coulomb stress means that here the tidal modulation is really dominated by normal stress effects, and so probably by poroelastic effects. And I'm gonna comment on the trends later. So this is the kind of observations we have. The first thing that I'm gonna show is how does varying the width of the fault zone box affect the signal tidal modulation. And so here the goal is to see if the signal of tidal modulation localizes along the fault or not. So we'll be looking at this magenta box here. All right, so at the bottom is the time series of modulation strength. At the top is the time series of the angular position of peak seismicity within the tidal cycle. And the color codes the width of the box. So just looking at amplitude for now, what we see is that for narrow boxes, we see a clearer increase in the tidal modulation. And then the strongest modulation is right before the main shock. For the wider boxes, we actually see a peak in tidal modulation around 2015. And this peak starts fading when the signal starts actually increasing in the narrow boxes. So here, I think that this may or may not be a sign of progressive strain localization onto the fault. I don't know yet, but I think that's an interesting observation nonetheless. And then in terms of the position of peak seismicity within the tidal cycle, the picture is quite complex. It looks like we're transitioning from one regime to another. I'm actually gonna switch to the results in terms of volumetric strain. Well, because they're very similar, but they're slightly cleaner and slightly easier to comment on. So it looks like, and this is very speculative at this stage, it looks like we are transitioning to something that is more stress control in the beginning, to something, to a long phase where it looks like peak seismicity is more around peak stress rates. And then at the end, and that's really speculative for now, I think that if we had maybe a better temporal resolution, we would see a transition back to stress control regime. But the main takeaway here is that the pre-main shock modulation increase is more visible in small boxes. And so that means that the signal seems to be localized on the fault. And that supports the hypothesis for the tectonic origin of this modulation increase. And when I say the tectonic origin, I mean, of course, the preparation phase of the Ridgecrest earthquake. So remains the question of the significance of these transitions between modulation regimes. I don't think these observations will be robust enough to answer this question, but I think that we can at least keep that question in mind. And now let's look at the results for all of the 5 regions. And I'm actually gonna switch directly to the results in terms of volumetric strain, just because they are so similar to the results in terms of Coulomb stress. So there is a long-term increase in modulation strength in the fault zone, and we observe a strong coseismic drop in modulation strength. As you can see, right after, in the aftershocks, the modulation becomes very weak. It looks also that there might be a shift in the modulation regime after the main shock. I think that here it's going to be hard to answer, to comment on the robustness of this observation. And part of the reason why I was speculating that if we had a better temporal resolution before the main shock, we might see a transition back to the stress control regime is because I think we might be seeing a stress control regime right before and right after the main shock. Okay, so also the signal in the southern part of the fault zone really closely mimics that of the entire fault zone. Although the southern part of the fault zone, it starts being quite complicated to study it because there are few events and so observations become very noisy. But they look very similar to the results for the entire fault zone. So I think that's a really important result here because it tells us that this modulation increase is not an artifact of wrongly located coastal earthquakes, right? There is just too much spatial separation between the two. And our earthquake locations are fairly good now. Also, along with the accelerating deep seismicity, I think that this supports, again, the hypothesis of a tectonic origin for the modulation increase. Now let's look at what's happening in COSO. We also see a long-term increase in modulation strength to some extent and somewhat of a coseismic drop. We only see that in the small box on the volcanic, taken on the volcanic field itself, but we don't see much happening in the larger box. And the modulation regime seems to be consistent across the main shock. So I'm going to comment more on that, but it looks like COSO is affected by the same process that affects the fault zone. And finally, there is this region that was defined in the just north of the fault zone where we just see weak modulation all along and no temporal evolution. And that's important because that allows us to say that the signal in the other regions is not associated with the large-scale drought that was happening in California at the time. Also, well, I wish I could comment on these features at the end of my study period, but this is actually corrupted by a data gap, which I'm trying to fix now. But I just can't get to download these 2 months of data in summer 2023 from the SCDC data center. So I think something is wrong with the data center. And if someone knows something about it, I'd be happy if they can talk to me. So I'm going to wrap up my presentations. First, I would like to say that the accelerating deep seismicity and the fact that the increase in tidal modulation localizes along the fault support the hypothesis that the fault zone is in the preparation phase of the 2019 earthquake, and strain is at a very advanced stage of localization. Also, I think that these new results clearly show that we're not somehow corrupting our results because of mislocated earthquakes that actually come from COSO. And I think there's still some more work to understand really what's happening with COSO, but I think that due to the spatial proximity of COSO with the fault zone and the fact that earthquakes in geothermal sites are highly sensitive to the tides, I think that it may make sense that COSO is sensing the tectonic process that is happening in the fault zone. And again, we just have preliminary results regarding the aftershocks. We need to finish the catalog and I need to deal with this data gap, but overall, it looks like modulation strongly drops after the main shock. So, okay, that's the main takeaway here is that the signal of tidal modulation increase seems to originate from a tectonic process. And some very generic conclusions before answering questions. I want to stress here that the detection of tidal modulation really relied on the use of a machine learning enhanced catalog. And tidal modulation in a place like Ridgecrest is very weak and complex. We don't really understand much about the modulation regime, at least for now. And I think it is time to build a model of modulated seismogenesis, including poroelastic effects. And in the future, I think that improving techniques to denoise or estimate of the modulation term will be essential to deploying these kind of techniques to different fault systems in the world. And really, this is an emerging field. Everything remains to be done. There is a lot to improve. So I think it's really exciting. So now, thank you for your attention, and I'll be happy to answer your questions.
Eric, thanks very much. Really great talk. I will invite people to unmute or otherwise join me in thanking Eric. Yeah, lots of interesting stuff. So while we give him a chance to catch his breath, I suggest that we use the raise hand feature at the bottom of your screen. And that will put us in an order to have a conversation. And I see that Hao's already raised a hand. That's great. Thank you so much. But absolutely want to encourage people to raise their hand and participate in the discussion. So Hao, please go ahead.
Yes, thanks, Eric, for this great talk. Sometimes the seismicity can be highly clustered. Do you do some declustering before analyze the tidal modulation? And do you think the declustering